Greetings and welcome. In this video, we're going to talk about the polar form of a linear equation. So far, linear equations, graphing lines, is very easy to do on a rectangular coordinate system, but it's quite a bit more difficult in the polar coordinate system. But we'll actually have some neat tricks in order to deal with it. So here I'm going to just give you what the equation is, and then we'll derive it in a moment. So it says the polar form of a linear equation where p is the length of the normal and phi is the positive angle between the positive x-axis and the normal is the following. So let me draw a picture of this so we'll be able to kind of figure out what's going on. So a normal, recall, would be perpendicular to the line that we're defining. Alright, so here's line L, let's say, and our normal is this perpendicular segment here. And it has length P, and it also has angle phi. Okay? And in the past we have defined the equation of a normal in a rectangular system being x times cosine phi. Let's see, is it minus? Plus. Oh, I'm forgetting now. Plus, sorry. Plus y times sine of phi minus p equals 0, where phi is the angle and p is the length of the normal. Alright, so that's for kind of the rectangular coordinate system. But now if I want to define this line at each point on this line in the polar coordinate system, this is the way we'll think about it. So here is a particular point, r comma theta, and I want to be able to have this defined dynamically. And remember that, right, so here would be r, and theta would be this entire angle there, right? And that would define kind of any point on this line. So let me just kind of fill out some relationships here. So the angle in between these two, right there, would be theta minus phi. Oh, I also have a hard time getting my phi vertical line to be sliced right down the middle. So that would be this purple angle here, and r would be the distance out. So you can kind of see how this might work out. So we've got p, we've got r, and theta minus phi we'll end up having to do some work with. But this is going to be how we represent it in the polar. Here is how this line is represented in the rectangular, defined by a normal. Alright, so if you need some more practice on normals, you can look up in your notes from earlier, or in your book, or even online. We're going to do a little bit of normal form work in this section as well. So let's actually take this normal form and see if we can derive this form here. So let's see. So the derivation of this would look like this. So if I originally have x times cosine of phi plus y times sine of phi minus p equals 0. Well, I can do some substitution immediately with x and y. Recall the following. I know that x is equal to r cos theta, and y is r sine theta. So I'm actually going to substitute those values in here and here, and I'll have r times cos theta cos phi plus r times sine theta sine phi. And I think I'll actually move this p to the right-hand side. You can see up here it's going to be isolated on its own anyway. Alright, so that got rid of our x and y, so at least we're in something that is represented in terms of r and theta. But I can actually do some simplification here, first of which I'm going to actually factor out this r and I'll have r times cos theta cos phi plus sine theta sine phi. Oh, actually, you know what I realized right there? This right there is not a phi. Let's see, fix that something like so. There we go. Now, this one is a huge callback. This is actually the difference identity for cosine back from our trig identities chapter. So that's actually going to equal cosine of theta minus phi is what I can substitute in there. And that is actually going to take us the whole way. So I'll have r times cosine theta minus phi is equal to p. And you can see that that's what we had defined up here. So, so here's at least some algebraic justification for where this formula comes from. And I just want to point out that in this formula, we have a couple constants. P is going to be a constant, as well as phi. So P and phi are constants. So that's just kind of an important fact. So those are going to be numbers for us, kind of like m and b in slope-intercept form of a line are going to be constants in that equation of a line where x and y are variables. And in our case, our variables are the r and the theta, right, are going to be our kind of dynamic components of this equation. And I just want to point out kind of the unique idea of defining a line, a whole line, based off of an angle and a distance. It'd kind of be the equivalent of, like, imagine if you were standing here with a tripod and, you know, kind of like a survey crew, and you're looking at a wall, and when I look at this angle, right, 0 degrees, it'd be a set distance. When I look at, like, 15 degrees, it'd be another distance. When I look at, say, 45 degrees, it'd be a set distance. And every angle I look at, I'd be able to get a different distance. I'd be able to kind of describe where that wall exists based off of all of my distances and angles, right? But it's kind of a really weird way to think about defining a line. But nonetheless, we have found a way to do that. So let's actually jump in and see if we can get some examples in here. And typically, our first type of problem is being able to convert from one form to another. So let's see. So write in polar form. So suppose I have this equation, 5x plus 12y equals 26. All right. So here's a standard form, right, of a linear equation, and I'm going to want to kind of convert this first of all into normal form. Actually, maybe I'll write some steps here. So convert to normal. To find p and phi, and then 3 plug into polar form. All right, so this is going to be our general approach. So let's see. So here, first thing doing, converting this to normal form. Let's actually figure out what A, B, and C are. Let's see. So my A is 5, my B is 12, and my C is actually negative 26. Our textbook's definition of standard form is AX plus BY plus C equals 0. So I'd have to kind of subtract the 26 from both sides in order to find A, B, and C. And in order to convert to normal form, this will be a quick review. I'm going to use this little equation here, plus or minus a squared plus b squared, square root of that whole thing. And the sign is determined by, sign is opposite of c, right? So this c term being negative, I'm going to use a positive version of this. And what I'm going to do with this formula is divide both sides of this equation by it. And that will get me started on my way to normal form. And then I'll have to, do a little bit of representation as far as figuring out what cosine and sine are respectively. So let's see. So let's do this. So this is going to be the positive square root of 5 squared plus 12 squared, right? So that's the positive square root of 25 plus 144, or the square root of, let's see, that happens to be 169. It's a very friendly number right there, which is exactly equals 13. Right, so what I'm going to do is now take this and divide it all through by 13. So I'll have 5x plus 12y minus 26 equals 0, and I'm dividing everything through by this 13. A completely legal move that I can do, right? Not changing the equality of the statement. So I've got 5/13 x plus 12/13 y equals negative, well actually I can simplify that, why not? Minus, and 26 divided by 13 I believe is 2, equals 0. So now this is in our normal form, and what I can gather from this, let me actually write down what normal form is again. So it's cosine of phi, or x times cosine phi, plus y times sine of phi, minus p equals 0. So the things that I'm interested in finding out are, I got to figure out what is phi and what is p. So p I can kind of define quickly here. P is going to equal 2. All right. So that's good for us. That's a win. And now figuring out what phi is going to be a little bit trickier. And what I first want to do is figure out what quadrant we're in. So thinking about what quadrant my angle of phi is in, I want to point out that notice both cosine, all right, here's cosine, is represented by a positive number, and sine is represented by a positive number. So the only quadrant in which both cosine and sine are positive in, right, they're both positive kind of in this quadrant 1. All right, so that's just something to be aware of, because my next move is solving the equation where I can see that cosine phi is equal to 5/13. Right, and sine of phi is equal to 12/13. So I can, cos inverse both sides here in order to figure out what phi is. But I just have to be careful of making sure which quadrant I'm in, so that way if I have a reference angle in another quadrant, I'll be able to then determine the actual angle, because it'd be very easy to get the wrong equation from here. So let's see, so what is the cosine inverse, let's see, of 5/13? So a bunch of other work there. So second cos inverse of 5/13, and let's see, it looks like I'm going to be working in radians here. So let me convert over to radians. And I get 1.176 radians there, right? So I get phi, switch colors. Phi is approximately 1.176 radians. Right? And if I did determine that I was in another quadrant, then this would have just been my reference angle, and I'd have to either, right, add or subtract it from 180 or subtract it from 360 in order to get the appropriate quadrant for it. So let's see. So I know the value of p, I know the value of phi. So now what can we do with that? Let's see. So I've just done kind of step 2 here. Plug into polar form. And polar form is this guy right here. Right? So I'll write polar form again for us. So it's p equals, let's see, r times the cosine of theta minus phi. And let's see, so plug in what we know, and I will get 2 equals r times cosine of theta and minus 1.176. And here, it doesn't look like it's all that helpful to us since this is a new form. But if I viewed the whole world from the view of an angle and a distance, this is how I'd represent a line. So let me append just one little piece onto this. What if I wanted to add part B, which was graph this? All right. So what I'd have to do in order to graph this is solve for r, right? Because our polar equations, in order to plug them into a graphing calculator, having it solved for one of our variables would be most helpful, and r is the variable we typically have solved for. And I could graph making a table of values or different things like that. I'm just going to show you quickly how to graph it using technology. But to solve for r here, I would have to divide both sides by this cosine. So I would get r equals 2 divided by cosine of theta minus 1.176. And let me graph this for us here. So let's see, switch modes. I'm in radian. Y equals, actually, is this, nope, that's a different version. 2 divided by cosine of theta minus 1 point, looks like I have a rounded version. What was ours? 1.176. 176, 1.1, oh, too many ones now. There we go. So there's my equation. I don't need to put parentheses around this denominator because it's a single function represented there. And when I graph it, notice I do in fact get a line represented here, which I think is like so crazy. I don't know. Like, I think it's pretty cool the fact that this line is defined based off of an angle and a distance in polar form, right? It's completely absurd in my mind. I don't know. Maybe you guys think this is normal stuff. A little play on words there, I just noticed. But it's not normal. It's polar. There we go. Let's see. So yeah. So there's kind of what the graph would look like, and it is in fact a line, right? And like I said, if you didn't have technology to graph this, you could do that with a table of values, something like that. I'll show you what the table would have looked like. Looks like I lost my focus here. So if I went to table set in the calculator, I believe, let's see, I could count by pi over 6s is usually a helpful angle. That's counting by 30 degrees, something like that. And if I go to second table, you can see how this is represented. And actually, won't work on this one, but there's something I want to point out. Yeah, it switches the value for r at one point because what happens, let me go back to the sketchbook, right? If I'm defining this based off of an angle and a degree, at some point I'm going to have an angle that's down here, and I would have to represent this point on the line with a negative value. Actually, you might have even noticed that when it graphed, it started here, graphed this, and then suddenly graphed this portion down here, because it actually represented these with kind of negative r values for when my angle was over here somewhere, right? And there's actually a point in which this function is undefined, and that would be the point in which I have an angle that happens to be parallel to my line, there would be no R value that should work for that, right? Because it's parallel and there's no point out there looking from the origin in that same direction that would be on the line. So it just wouldn't work out in that capacity. All right, let me do one more quick example, I hope, of the other direction here. Let's see. I gotta reselect my pen. So let's do an example of right in rectangular form. So suppose I have the equation 2 equals r times cosine of, let's get a better parenthesis there, theta minus 60. All right, so this one appears to be in degrees, and I'll even put a little degree symbol there. So we can gather some information from this, right? You could tell me that, right, in terms of if you wanted to graph this, that this would be 2 units away, 60 degrees would be the normal, right? And you could probably draw the line rectangularly pretty easily using normal form by finding the values of p and phi, right? But now I want to write this in rectangular form. I'm going to have to deal with this cosine issue here. And let's see, the way I'm going to deal with it is, you might remember this trig identity for the difference identity. We actually used it previously in our derivation of this formula, or form rather. Let's see, and it's cosine alpha, cosine beta, and I believe if this is minus, this will be plus, if I remember correctly. So sine alpha, sine beta. There we go. So using this trig identity, I'm going to rewrite this. All right. So let's see. So I'll have 2 equals r times, and I'll have cosine theta cosine 60 plus sine theta times sine of 60. Right? And I can now evaluate some of these, right? So this is 2 equals, sometimes my r's look like square roots, I find. So this is cosine of 60 degrees is square root of 3 over 2. Yeah, there's an r and an r. Square root, radical sine, I guess. Times cosine theta plus, oh, I just said that wrong. Cosine is not root 3 over 2 at 60 degrees. Silly me, silly me. Cosine's going to be a half. All right. And sine of 60 is root 3 over 2. Right? So I've got that. And now I could distribute this r into it. It's actually, I'm doing kind of exactly the opposite of what I had done during my derivation. So I'd have 1/2 r cos theta plus rad 3 over 2 r sine theta. And hopefully, being in this chapter, you guys can recognize what these can be substituted for quickly. And I would get 2 equals 1/2 x plus rad 3 over 2 y. And this isn't technically in standard form yet. I'd have to then also multiply by 2 to get rid of the denominators there, because standard form is just a fan of non-fractions. And I'm actually going to switch the sides here too. So I'll have x plus the square root of 3y equals 4. Right, so there is a standard form for that equation. Oh, actually, what do you know? I put it in the form that I'm used to calling standard. We'll actually move this to the other side, since that's what we're used to. Oddly enough, I'm used to another form that's standard, but that's okay. Really, pretty much the same thing. And if I wanted, I could solve that for y equals mx plus b, do all sorts of stuff there as well. All right, well, thank you for watching. So today we'd looked at finding the equation of a line in polar form, which still, I think, is one of the coolest things that they're able to do, mathematically speaking. So thanks for watching, and I'll talk to you guys later.